Hi, I'm Eric Grolke, and we're going to be doing a problem today for Chemical Engineering 455 for the fall term in 2018. We're going to be talking about problem number 1, which is generating electricity from wood pellets. To do this, we're going to use a steam cycle. Typical steam cycle that we've already learned about in thermodynamics. So this portion of the discussion is some theory, the efficiency of the cycle that we expect, what equipment we're going to need, and how we might set that up. Then we'll have a separate piece on how to do this in the simulator. The reason we start with this problem is because we really have to solve it by hand first before we put it in the simulator, in particular because we need to know what we typically know what the enthalpy and the entropy is of the various streams, but we need to convert that into pressure, temperature, and flow data for the simulator. So we're going to do the theory and some of the discussion first, then we will move to the simulator. So to do steam cycles, basically, a key piece of the theory is the Carnot cycle. And Carnot was a Frenchman and came up with this ideal fluid cycle in 1824. This is the age of the steam engine. They had to do better design, have better understanding. This was really important. The one we're actually going to model in ChemCAD for our problem is the Rankine cycle. And we'll see what the reasons are for that when we go through this. Basically, what are some examples of using a steam cycle for generating power? One is we're going to use biomass to make electricity. Another, which was very popular in the 1900s, was, and particularly for the Navy, was to use a steam cycle. The heat source was diesel fuel, and the energy output was electricity for the boat, but also electricity to drive the turbine, or even just power the turbine shaft directly. So they used a cycle to get to generate steam. The steam went through a turbine and was a direct drive into the propeller system, and then they also powered the electricity on the boat. I have some slides from the USS Wisconsin that was designed on this property that I think you may find interesting. So let's talk first about the theory for the Carnot cycle. There are a couple important parts. One is that the power produced is a function of the temperature difference between the heat source and the cold source. I'm going to sketch this system in a minute to remind you what it looks like. And basically, as the temperature difference goes up, this implies more power. So what we'd like to do is we'd like to have as high a heat source as we can and as low a temperature source as we can have as well. So let's draw a Carnot cycle quickly here. Here is the high temperature, T high, and then we're going to put in heat because we're going to burn our fuel. We've got a working fluid. The working fluid is going to come in here as a liquid. When we heat this up, we're going to generate a vapor. We're going to have a expander here, or a turbine. The fluid is now a vapor. So we're either going to be interested in shaft work, or we can turn that into electricity as well. When it goes through the engine, it drops in pressure and in temperature. And then we come to the heat exchanger to cool this further. This is the low temperature, and the cold temperature. And let me put a little dot over here to indicate that we have a heat rate here. So this is still a vapor. What we're going to do here is we're going to remove some extra heat. We now, if we want to recycle the fluid, we need to get it back to the liquid state. So this is going to come back out of here as a liquid. And then we recycle it. So, and basically in our system, this working fluid is going to be water. So that's the Carnot cycle. And we know that if we have a very high temperature here and a very low temperature there, that will give us the highest efficiency. And in fact, let's go ahead and write what the efficiency is. And we'll do that in, see if yellow is a good color for efficiency. So in theory, the efficiency is going to be the net work out divided by the heat input. And what you can see here is that we're putting in so much heat, but not all of it gets into the work of the shaft or the turbine. And so we're rejecting some heat down here. So let's go ahead and write this efficiency is the net work out. The net work out would be the shaft work divided by the amount of the rate at which heat is coming in. If everything is absolutely ideal, there are absolutely no losses, then the shaft work is simply the high temperature heat rate minus the low temperature heat rate, cold, yes. Let me fix this here. This needs to be a C. And so the efficiency then is 1 minus the cold divided by the high temperature rate. Okay. Now we need to get this into 4 process steps. So the first thing we need to do is, let's start here. And I'm going to start labeling the stream for the working fluid. Let's say this is stream number 4. And I'm doing this because eventually you want to take this to the simulator. We're going to label the stream numbers. We're going to label the equipment numbers here. This will be point number 1. Point number 2 will be coming out of the furnace that we are using to generate the energy. Point number 3 is after the turbine. And then point number 4 is the liquid again. Okay? So, let's talk about how we want to do this. Well, we're going to label the equipment. Try to do that on the same diagram. So if we imagine this to be an ideal system, we would like to heat up the working fluid by using a furnace. So number 2, this would be a furnace of some sort. So I'm going to put 2 furnace. The circle means that it's a piece of equipment. The turbine, I'm going to make a piece of equipment, number 3. The heat exchanger, I'm going to make equipment number 4. That's the heat exchanger. And then what's happening through this process is that we have a high pressure and high temperature here. This becomes a low pressure and low temperature by the time it's gone through the turbine. But it is still a vapor. We now need to condense, when we've condensed it here, it is at a low pressure. We have to increase the pressure. So this is going to be a pump. That's going to be number 1. So we'll be able to accomplish this cycle by using a pump to raise the pressure of the liquid, a furnace to heat it up to a vapor, a turbine to capture some of the energy from that, put it into shaft work or make electricity, and then cool down the rest and generate a liquid again, which is then recycled. Okay, so that is the essence of the steam cycle. Okay, so we want to do 2 quick example problems to help us think about what we need to do to design one of these power plants. The first one is, let's get an estimate of efficiency for typical conditions in a steam cycle power generation facility. So here's the problem. We're going to work with the water as the process fluid. Well, let's put up some conditions on water. Let's take the critical conditions, because remember, we want to get to a high temperature, and we'd like to know, are we going to be supercritical? What are we going to be? So let's take some typical critical conditions for water. Its critical pressure is about 220 bar. Its critical temperature is about 647 Kelvin. Its critical volume at that point is 322 kilograms per cubic meter. And remember, the density is about 1,000 kilograms per cubic meter, so it's about 1/3 the conditions. A typical set of conditions for a steam power plant might be the temperature of the fluid at the very high end is, let's say, 600 K. Let's just choose that. The temperature at the condenser might be 293 K. So I've made this subcritical because the temperature is not too high. So let's do the thermal efficiency. Thermal efficiency then is 1 minus 600 over 293, which equals 51.2%. Okay. Well, normally we wouldn't be too much interested in a supercritical process because the costs go way, way up. But look at this. If I'm going to be under the supercritical point, then my efficiency, that is the amount of energy I get out into the shaft work or to electricity, even under perfect conditions, is only 51%. For energy production, this is really not acceptable. So we are going to be probably operating this above supercritical conditions. For example, we might be operating this at 750 or 800 K roughly, and that'll give us a much better number for efficiency. So that's one thing about what the high temperature is. Let's talk about the cold temperature. The melting point of water is 0 degrees C or 273 Kelvin. And so as a practical matter, we can't have a temperature much less than, certainly not less than 273, because the problem with that is going to be tremendous heat transfer problem to a solid. Maybe we can get clever and figure something out, but it hasn't happened yet. And so we need to be close to this temperature as the rejection point into something else. What do we use to remove the heat? We often use, if it's a small system, we might use a pond, but more likely, for a large system, if we want to make a big plant, we're going to use the ocean or we're going to use a river. So let's talk about a specific plant site that we might want to have. And let's suppose we orient it in Kentucky. What would be the biggest river? Well, the biggest river would be the Ohio River. Let's put up a medium-sized plant, which would be 800 megawatts. Okay? And let's suppose that this thing is at, and let's suppose we use these numbers, 600K and 273, and we now know that we have to put in the thermal efficiency of the whole plant, and let's suppose the actual thermal efficiency of the equipment is 70%. Okay. The highest we can get for thermal efficiency for this temperature drop is 51%. So if our plant equipment only is 70% efficient, then the actual plant efficiency is going to be 0.512 times 0.70, or basically on a percentage basis, 35.8. This is usually not going to be acceptable. So we are going to have to do better than that. The other quick example problem we would like to do is an environmental question. So this is really a thermal efficiency question. Gets at climate change, et cetera, power source. And then the next question we have is an environmental question. Okay, if we're going to use this plant, are we going to raise the temperature of the river very much? Great question. We're going to have to answer that question in the environmental impact when we put the plant requests forward. So let's figure this out. So if we, the best place to site this is a fairly large plant. The best place to site this would be, let's say, on the Ohio River. Let's choose a spot. Let's choose a spot where we know the river flow rate. Well, we happen to know the river flow rate for the Ohio River at Greenup, Kentucky. Okay? And that is, I'm going to give it to you in cubic meters a second. That's just under 4,000 cubic meters per second. That's pretty good flow, right? Okay. So what I'm going to do to figure this out is we're going to just use, we're going to find out what the condenser cooling rate needs to be. And we're going to say that's equal to the Q that's going into the river. So we're going to have the mass flow rate, which we know. That's this one. We know the heat capacity of water, and we know the delta T. Okay, or actually we're going to solve for the delta T. So Q sub C, after I do a little work to convert, after we've designed the plant, we have a Q sub C of about 1.4 million kilojoules per second. C sub P is 4.18 kilojoules per kilogram degree K. And so we can now solve for delta T. Excuse me. We're going to go right from volume to weight here. And we come up with an answer which is about a tenth of a degree Kelvin. And you look at that and you say, hey, this is not a problem. What are we worried about? The environmentalists have nothing to worry about, because we're only going to heat up the river at this flow rate by a tenth of a degree Kelvin. This is not very big, is it? And look at the flow. Well, there's a couple things wrong with this approach. The first one is the flow is going to vary, so you need to look at this over time. Look at from January to December, temperature, blah, 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 and get what the variation is going to be. The other thing is, this is going to be the average variation for the river. If you look at how stuff is going in the river, here's my river with the banks. Someplace in here I'm going to have a heat exchanger, or maybe I have it out here. Maybe I take river water and run it through an exchanger and then put it back in. But let's say we take a stream out and then we put a stream back in. This stream is going to have a plume associated with it. So at some point, it's going to be higher than 1 degree Kelvin. So it's, you can begin to see the importance of efficiency, equipment size, equipment operating conditions, what's the temperature going to be, and then how am I going to reject the heat for a large plant. So these are all design issues that we're going to have to deal with in the design of this plant. Okay, so what we're going to do now is we have some constraints, some design constraints laid on this system. Now what we're going to do is start looking at a typical way to design this, which is to use either TSH data from steam tables, I'm going to provide steam tables to the class so that you can, if you want, your team can do the design using a steam table. Or you can use a TS diagram. I'm going to give TS diagrams to the class for water. The key reason to do the working fluid as water is we have tremendously good pressure, volume, entropy data on this fluid. We've been using it for several centuries. And so we know these values, the thermodynamic values, well. Other fluids, we would have to use equations of state to get us. We actually use some advanced equations of state for water to do this. So let's start talking about options in designing the equipment and what that's going to mean in terms of efficiency and so forth. And to do that, we're going to use TS diagrams. Okay, so let's start out with a typical Carnot cycle on a TS diagram, and I'll show you very quickly why we don't use it, why we use a Rankine instead. So here is Carnot cycle on a TS diagram. Here's the two-phase region for our working fluid. The vapor is over here, the liquid is over here. So what we might do is we might say, okay, we're going to have a low temperature. And let's suppose I started down here, and this is the liquid coming into the pump. This will be 0.4. I'm going to put this into the pump. Let me put this in a different color. Put this into the pump, raise its temperature and pressure. I'm going to then put in Q. I'm going to then take out shaft work. And then I'm going to reject the unused, unrecoverable heat. So that's stream 4. This is stream 1, stream 2, and stream 3. Okay, why don't we use this for a fluid? Well, one of the problems is happening over here, and it's all associated with equipment design. Basically, we would prefer for the turbine, we would actually like to prevent condensation. Although we've drawn these as ideal isentropic steps, 4 to 1 and 2 to 3, you notice they're in the middle of the two-phase region. It's going to be very hard to design a turbine that does that well. In particular, when we have fluids, liquids hitting the turbine blades, that can cause pitting, corrosion, and it's very low life. This equipment is going to be expensive. We need to have it for a long period of time, and therefore we have to present condensation. So what we're going to try to do is we're going to try to operate these systems such that we have the turbine always in the vapor phase. Never any liquid, or very little liquid anyway. There are things we can do to adjust that in turbine design, but in general we'd like to have it far away from condensation. So now we're going to go from the Carnot, which I've drawn, and I'm going to draw the Rankine, which is slightly different. Okay, so let's get down here and work on the TS diagram. All right, so my condenser is going to give me saturated liquid down here at 0.4. I would like to put that into a pump, raise its pressure. I'd like to do this system in 2 steps. we're going to go from a low temperature and pressure to a high temperature and pressure over here. That's supposed to be isothermal. So what I'm going to do is I'm going to pump it first, and it's not going to take very much temperature rise. So now I'm at 1. Then when I start putting it through the heater to heat it up, I'm going to heat through a number of steps. I'm going to heat it up as a liquid. I'm going to vaporize it. And then, so this is at a higher pressure. So I'm going to heat it along an isobar. To a higher temperature. And I'm going to heat it up, as we said, we're going to heat it up so it's supercritical. No question. It's going to be up here. Because when I condense it, I need to condense it down to a lower temperature. This is going to be a isentropic condensation. When I put it through the turbine, I don't want to condense it. This is going to be an isentropic turbine. The ideal would be something like this, going down to there, meaning this isotherm, where I'm removing heat. We know that the turbine is not going to be isentropic, and so we're actually going to, the actual curve is going to look something like this. Maybe. So this is going to be a real turbine. With some efficiency. Don't know what that is. The pump. We're going to put some energy in to the pump, but this is typically only about 1 to 3% of the total energy in this system. Okay? Well, that's pretty good. Let me label the points. This is 2. So in the furnace, it's going to go, we're going to pump it up to a high pressure. This pressure, these 2 pressures are the same. Pump it up to a high pressure and then change the temperature. So that's how we're going to calculate the change in enthalpy and entropy of the fluid. And remember, we're actually making micro changes if you want to think about it that way. Then here, we're going to put it through a turbine so that it is still a vapor, or maybe just condensing as it comes out the back end of the turbine. And then this, so that's 0.3. And then this is the heat exchanger. So I'm putting in heat here. I'm going to take out heat here. Okay, well, this is nice, but we can quickly think of improvements. One thing is we are heating the fluid up to this temperature and pressure. We're taking it in one step, but we are constrained here by the need to try to prevent condensation in the turbine. So people have generated another solution, which is called the Rankine cycle with reheat, and this uses 2 turbines. One, a high pressure turbine, so it can heat it up here, drop down to maybe there, and then what if I took this same fluid, this is at a lower pressure, and heated it back up again in the furnace? So I'm going to do this heating and energy recovery using the turbine in 2 steps instead of just one, because the one is constraining how much energy we're getting out. So let's talk about then the Rankine plus reheat. Okay, so here's our TS diagram. Okay, let's see if we can draw this system then. We're going to take things, here is point 4. We're going to increase the pressure up to the working pressure. We're going to boil it, take it up here. We're going to take it down, let's say from here to turbine number 1. Turbine 1. High pressure turbine. We're going to take the same fluid, heat it up again. Maybe it's the same pressure, maybe a little bit different. I mean, same temperature, not the same pressure. Here's the second turbine. Then we will take the fluid back and condense it again. Okay, so for example, on a steamship, and particularly like a Navy steamship, if we're going to do a Rankine steam cycle, we will use a pump. We'll have 2 turbines. We'll have a high pressure turbine, a low pressure turbine. The difference in pressure is probably on the order of a factor of 4. So if this is like, well, we'll get to the pressures later when we do the actual problem. But this pressure difference may be a factor of 4, so this will be running still the same temperature coming in, but running at a lower pressure. Therefore, you're going to extract less energy from the stream, but you're still getting that energy out, which you didn't get out before. And then you're rejecting heat to the low temperature side. And so this improves the efficiency of the overall system terrifically, and it recovers critical heat. The places like the Navy is very interested in how much can we get out of the fuel. And of course, now that we are very sensitive to the use of electricity and conserving and so forth, using a Rankine with reheat to give us 2 ways to generate electricity and increase our efficiency is great. We also, the next step from this is to go to a cogeneration process where you do this, but you also, in addition to generating electricity from a turbine, you want to generate steam for process conditions or regional or local heating, those kinds of things. And so that's a cogeneration process. We're not going to model that. We're going to stop here with a Rankine plus preheat. But when you're designing your system, we're going to ignore the Carnot cycle. We're going to start with a Rankine cycle, 1 turbine, and then we're going to consider what happens if we use 2 turbines in terms of efficiency, cost, etc. One of the things that we want to get to is sensitivity analysis of these systems. So in our design, we're going to have to get equipment size. We're going to have equipment cost. Okay. We're going to have to get efficiencies of these. Come on. Psst, I did it again. Process efficiency for the whole thing. And we're going to have to do some economic, we're going to do some economic sensitivities. You notice I'm not quite calling this optimization yet, okay? And we'll talk about how to optimize as we're going through the problem. But we're going to have to do sensitivity of equipment size, interested in power coming out, capital equipment, purchase equipment costs, for example, total capital investment, the utilities that we need to do this, including how much fuel, and then we're going to try to look at the sensitivity of our output or our costs to plant size, efficiencies of our equipment. So we have all these things that we can do to improve this process. Once we get the process designed, type A, that's plan A, plan B is this. Once we get one of those things run, then we're going to want to do a number of sensitivity analysis to improve the process in terms of cost, efficiency, whatever, fuel use, we don't know yet. And we'll have to see as we go through the problem exactly how we're going to think about improving the initial design, whatever we decide to do. And that we're going to do with the simulator. So the reason to get to a simulator is once we actually have a reasonable design, we're going to want to do a lot of what-ifs to figure out exactly what's going on and the best process we can possibly make. Okay, I think this is a reasonable stopping point for the Chalk Talk part. And I think what we're going to do now is go to the process simulator and actually build one of these processes. I've got an example from a textbook on a ranking cycle. So the thing we're going to put into the simulator is the ranking cycle plan A. Plan B is Rankine plus reheat. But we'll put this in, and that'll be a good first step in doing the simulation. Then we'll have a very good comparison in terms of costs, efficiencies, etc., between the Rankine Plan A, just the single turbine, and the high pressure and low pressure turbine system. With those, we'll get a much better feel for which one of those is going to be efficiency. I'm pretty sure this is the one that you're going to like and you will want to do eventually, but for your report, you'll want to have a nice comparison between these two. So we're going to set this one up first. Thank you.